questions about elimination thus far? Okay. Show the expected product for this reaction. Okay. First question for us, is this substitution or elimination?
Elimination.
Because we're going to start more and more, we're going to consider both. Just because this is the elimination handout doesn't mean we're not going to be doing some substitution along the way. Got to keep substitution in mind. Is this substitution or elimination? Okay. Maybe we're beginning with a substitution reaction in these problems. Did you consider substitution or elimination?
Elimination.
Anybody? Substitution? Why substitution? What's your argument? What's your thinking? We got hydroxide, strong or weak? Strong. Tetrahedral carbon with a leaving group. What type of carbon is it on? Primary, secondary, or tertiary?
Tertiary.
Okay. What type of reaction is this? Is it substitution? Why is it not substitution? So if it was substitution, it would SN1. Well, this has a strong nucleophile base. It's going to it's going to be involved. So it won't let it be SN1. It's going to be bimolecular. So is it SN2 or E2?
E2.
E2, correct? You can't do SN2 on tertiary halide. We know it's bimolecular. You can't do SN2, so by default this is an E2. Yeah? Okay, so what's your product? Anybody have a product, E2 product? Anybody have a product? I see a lot of people trying to work the problem. I would have expected that you might have done that before class. Anybody got a product or a question about reaction? Question?
So that anti-Coplanar is much more cyclical type. So how does that truly affect does it affect the rate at all? Whether it's anti-Coplanar or cyclical?
Yeah, it affects the rate. Which one's preferred? Yeah, that means rate. It's going to be easier, thus faster. Yeah. Okay, how many different theoretical elimination products are possible? How many different? I hear two. Anybody?
Three.
One way to approach it, if you're looking for what's the product, you could first by start, okay, what are all possible products? Reasonable theoretical product coming from a beta elimination, I think the answer would be 3. And I'd recommend that you maybe have drawn those. Or you can just approach it, I'm just going to draw the right one. If you're unsure, maybe draw all 3 and then decide. That's going to take more time, but when you're doing homework, you get time. And then look at the 3 possible theoretical products. I think there's 3. Okay. For example, we could have, where do we have beta hydrogens at? Here's the carbon. Where's the beta hydrogen? You got 3 beta carbons. You got carbon here, and carbon there. That beta carbon doesn't have any H's on it. But this one has 3. That one has how many? 1. And it's some stereochemistry. It's going back there, right? Okay. This has 3. I'll just draw 1. And we don't need to show any stereochemistry. There's 3 there. Okay? If you remove this H, let's call that HA, and this one HB. If you remove HA and do a beta elimination, put double bond between this carbon and this carbon, the product will look like what? Okay, if we lose HA, you do a beta elimination and the bromine, you eliminate HBr right there. Does that look like the product? If we put the double bond in between that carbon and that carbon? This carbon will have, double bond will be there, and this carbon will have 2 groups. It will have the tert butyl and this group. The carbon has a tert butyl in that group, yeah? Okay. Is that Sasef or Hoffman product? Yeah, that's Hoffman. That's not the most substitute. What if we remove the HB? What would the product look like? Well, put the double bond between these 2 carbons, yeah? I'll just write here for space. Maybe you have somewhere else if you want to write ultimately the product here. I'll run out of room over there. Maybe I can come over here. Double bond between these 2 carbons. Carbon on the left will have what on it? A methyl and an ethyl. Is that right? This carbon over here has a methyl and an ethyl. But since it's now trigonoplanar, there's no more stereochemistry. It's now planar. Nothing's going forward or back now. The carbon over here, which the leaving group is on, has what groups on it? A methyl and a tert butyl. A methyl and a tert butyl. But hold on, why did I draw the 2 methyls trans and the 2 ethyl and tert butyl trans? Could it also be a possibility of the ethyl and the tert butyl being cis and the methyls being cis? Basically, this alkene is stereogenic, and we could have the stereoisomer. That alkene is not stereogenic. So this would be minus HB. Okay, there's the 3 theoretical products, I think. Anybody see something else? Another possible elimination product?
I just had a quick question. So because it prefers anti-coplanar, would it be possible for the bromine to kind of rotate? So
Yeah. We haven't got there yet. We're going to have to do that. The next question is, which of these 3 is going to be the product? And now we've got to start considering that, because what is a requirement for E2 elimination? It's at the very top. Okay, there you go. Question, what type of base do we have? Is it sterically hindered?
No.
No. So this base will give the, what do we call that product over there? There's stereoisomers of it, but it's the, how do we want to spell Sasef? Is it S or is Z?
Z.
You spelled it with an S before?
Yes.
Sasef. Sasef has stereoisomers. So we have to think more over there. KOH is a very small base. It's going to have no trouble giving the Sasef. But we still have to make sure we meet the stereochemical requirements. How do we do that? Best way to look at this is Newman projection. Okay? I'm going to not think about HA. Okay? Because the base is not sterically hindered. There may be other reasons to discount it, but that's the reason here. This base can take HB, even though it's more crowded. You see how it's more crowded sitting in between the ethyl and the methyl? It's more crowded. It's okay, KOH is real small. Let's get rid of this. The real question is which stereoisomer over there, or the question now becomes which stereoisomer we're going to get. Which one do you think we're going to get? First or second?
First.
Why the first?
Because the larger groups are trans to each
Yeah,
other.
but that's not what we look at. We got to look at this top thing over here. We got to look at the stereochemical requirement. We don't just say we get the best of those. We only get the one in which the stereochemical requirement is met. How do we do this? We got to look at the anti-coplanar. When it eliminates, the H and the BR need to be like this. That's most preferred, and if it can achieve that, that's going to be the most preferred. That's how it's going to. Okay? Can we draw this looking like this? Yes. Circle, circle, dot, dot. Okay? Basically, we're looking down this bond here. Okay? You want to stand on the left or right? It doesn't matter. I'll stand over here, I reckon. Okay? We're looking through there. Carbon in the front, carbon in the back. Front carbon, something going straight down. What's going straight down?
Tert-butyl.
Tert-butyl. Okay, we're going back to test 1. What's on this carbon to my left if I'm over here?
The methyl group.
The methyl. I'll draw that as an ME. What's over here to the one behind the board?
Bromine.
Bromine. That's the front carbon. Now let's look at this other carbon over here. What's going straight down in the plane?
Methyl group.
Methyl. Uh-oh, the tert-butyl is also going straight down in the plane. The methyl is what? Eclipse, just right behind it. Let's draw it a little bit to the side. It's right behind it. Okay, what's on that second carbon coming to my left?
Ethyl.
Ethyl. It's right behind the methyl. And what's on this other carbon going back? The H. And that's the H, what? HB? What was it? HB? Yes. It's right behind the bromine. What's the current relationship between the bromine and the H that's going to get eliminated?
Coplanar. Syn coplanar.
They are coplanar. The plane is right here. They're right behind each other. If you lay a piece of paper across my arms, it's a plane. But is that syn or anti-coplanar?
Syn.
That's syn coplanar. What needs to happen? One of those groups needs to rotate and go like this. Same plane, but opposite. We can rotate the front or the back. I'll rotate the front. Let's rotate this, and let's put the bromine here. There's bromine here. What else is on the front? Tert-butyl. Where's the tert-butyl go when I do this? I'm rotating this.
Go straight. Oh.
How many degrees?
180.
180, yes. Where's the tert-butyl go?
At the top.
Tert-butyl goes straight up. And what's the other group on the front? The methyl?
The methyl.
Methyl is here. The back did not change. That is, the back is HB. And what else is in the back?
Ethyl.
Ethyl and
Methyl.
methyl. Is that right?
Yes.
We have 2 methyls, one on the front carbon, one on the back. There you go. It can rotate. Now look at the bromine and the H. What are they?
Anti-coplanar.
They're anti-coplanar. Okay? H directly that way, bromine directly this way. H directly this way, bromine directly that way. That's when the elimination will take place. The hydroxide takes the H, the electrons move in, they can't see it, they move in between the 2 carbons and kick this off. Okay, but you can't see the two carbons there. So they're like this. But here it is. All that's concerted. Right? Bam! There's your product. Well, guess what? If that takes place like this, these two groups are adjacent to each other, and these two groups are adjacent. The methyls are on the same side when the reaction takes place. Thus, they're going to be on the same side in the product. Which product do we get? First or the second? Second. The methyls are on the same side. Butyl and the ethyl, okay? Because it has to eliminate like this. It can't eliminate, well, it could. Does it say syn coplanar cannot happen? No, it says one is highly preferred. Which is highly preferred?
Correct.
Yes. And that's the one it's going to eliminate. And we can add other comments here, but it's at some point we just need to sort of end it. Because you can keep going forever. That's the way we want to do it here. And so we see, did we get the most thermodynamically stable product?
No.
No, that's the other one. As was pointed out, the bigger group's trans. Isn't that more stable? Yeah. You don't get the most stable product. Now, this is more stable than that, the other one, because at least this is tetrasubstituted. That's why it's Satesep. They're both tetrasubstituted. The other one, Hoffman, was what? Disubstituted, I believe? Yeah. So, what mechanism did we do here? E2? Everybody agree it's E2? Or E1? Why is it E2? Strong base, right? Strong is going to be bimolecular. Question. What if this was somehow an E1? Different reagents. What if it was E1? What would the product be? What product is formed by an E1?
Satesep always.
What?
Always Satesep. The Satesep product? Always the Satesep product?
Yeah, but we got two Satesep products, so we need more information.
It's the most stable.
What's formed with E1?
That first one.
What's the statement for E1? It's probably in bold.
Thermodynamic.
Always gives the most stable.
Right, but again, we got two that are most substituted, so how can we decide? What does it say? The most stable. So which of the two over there is most stable? We've already said. This would be the E1 product. If the reaction was done by E1 mechanism. But this example was the E2, so this first reaction gives the one with the E2 product. Okay? Questions about any of that? All right, you can do the second one on your own there. Let's move to a ring. Here we go, substitution elimination. What do we see here? Any questions about anything here?
Yes, sir. What does T stand for?
Great question. TEA?
Yes, sir.
Triethylamine. Triethylamine. Have we mentioned that before? Yes, previous handout. What did we say about triethylamine? Anybody remember? That was a passing comment. Well, you got it? What did we say about it? It is considered strong. Even though it's neutral, we can consider it strong. Okay? So it's going to want to be bimolecular, either SN2 or E2. But what else did we say about it? Did we look at nucleophiles in the previous handout? I think you went the wrong way there. By the way, I did send out an answer key to problems of the substitution. Let me know if you have any questions about that. I think there's lots of good problems there, including the mechanism reaction that was done by Louis Pasteur. Reaction with quinine, pretty straightforward mechanism, but you have to
It's an
see what's
non-nucleophile
going on.
base, such as E2 reaction.
Anybody got it?
Yes, sir. Is a non-nucleophile base such as for E2 reaction.
Oh. It's commonly used as a non-nucleophilic base, commonly used for what type of reaction?
E2 reaction.
E2?
Yes, sir.
Okay. Yeah, that's what it is. It's triethylamine. It's an amine with 3 triethylamine. Okay. It's strong enough to be a bimolecular strong base, but it's sterically hindered. It's got these wings on it, so it's not going to be able to come in here and do a substitution. It's commonly used for E2. Okay. What is THF? Just a common solvent. And THF actually was not on the solvent list I gave you during week 1, physical properties handout. It wasn't there. It's kind of common, but I didn't put every single solvent there. Called tetrahydrofuran. It's an ether, cyclic ether solvent. Similar to diethyl ether, but it's a little bit better solvent than diethyl ether. So just solvent, but this is your base here. Okay, we're doing the E2. We kind of said that. Commonly used for E2. It can do E2. It is strong enough. So what's the product here? What's the E2 product here? How many theoretical products are possible? We've got an H here, and it's bolded, right? HA. On this beta carbon. The other beta carbon, there's 2 H's. I'm going to draw them both in. HB and HC. How many theoretical products are possible?
2.
Right? But don't confuse, those H's are the same, so don't think that's going to cause any difference. How many possible products?
2.
I didn't hear you about 2? Yes. What are the 2? We can put the double bond in here. That is removing HA in the leaving group, and the alpha group is here. That's it? I mean, the 2 H's are still up there. I just won't draw them in now. Everybody agree that's it? Note that this is now planar. All the time you guys will show this with still being like dashed or bolded. The carbon now, since it's alkene, is now planar. It's all in the plane. There is no dashed or bold anymore. Right? Okay? But what if we remove one of the other H's? And I'm not going to just consider them the same. And they are, I just labeled them there. That would be what? Put double bond here. Remove HI there. This down here remains tetrahedral. No change at all down there, right? Double bond put up there. I'm not showing you any of the H's. Are those the 2 products?
Yeah.
Question. Does either one have stereoisomers that we need to consider? Is either one of these alkenes stereogenic? No. Let's test 2. No.
Flip it, it's the same thing.
Neither one is stereogenic, correct? Not in a 6-membered ring. There's no stereoisomers here for these alkenes. Okay, Which of these out? So the answer is two theoretical products. You can either remove HA or one of the other H's up there. There are two. Okay. So which product are we going to get? Label Satesef or Hoffman. Which one's Satesef?
Left one, right?
That's Hoffman. Everybody agree?
Yes.
Which one are we going to get here?
Two.
Hoffman.
Why Hoffman?
It's a
We need to consider a requirement here.
sterically hindered.
High preference. You'd like to first get maybe the Satesef. That's the most stable. Can we get Satesef here? Well, that would require moving this H. Is the H and the leading group anti-coplanar? Or can they be? Keep this in mind. Anti is similar or synonymous with trans. Anti-coplanar, trans-coplanar. Okay? We noted that. Anti or trans-coplanar. Is this H in the iodine trans? No. So they will never be trans-coplanar. And we can look at a model. Everybody agree that the I and the H are cis?
Yes, sir.
Well, let's make a 6-membered ring. And let's put two adjacent groups. I won't put the alpha group on there, but iodine red, I reckon, and the H green, HA green. They're cis, okay? Here we go, we got a nice chair confirmation. Iodine is straight up. I see the iodine straight up over there? No? How's the green H? Is it straight down in the plane?
No.
Here's the plane. See that right there, guys? Straight up. The H needs to be here to be straight down and in the plane. Everybody agree? How will it ever get there?
Okay.
Well, you can't disconnect, then you're going to go from cis to trans. That's a different compound. How about a ring flip? Okay? By the way, what did we say? The leaving group has to be in what position to? Did we say it had to be axial?
Yes.
We said that. I moved it equatorial. Do you think we're going to get any good results? No, I've already told you that. Okay? Look, now it's equatorial. It's straight up. Is the green straight down? Anticoplanar? No. It never will be equatorial. Possibly axial, but only in this case if the H is trans. Because it makes sense, guys, right? You can only call it transcoplanar if the groups are trans. And clearly they're kind of cis here. So in that regard, the ring makes it a little easier. What about one of the other H's that's available? Or is one of those, can one of those be anticoplanar, transcoplanar? Which one can be?
HC. HC.
C? Correct. Let's look at the other carbon, the other beta carbon. Okay? I'm not going to take time to put color. Here are the other two. Which one can be transcoplanar to the bromine? That one, which is equatorial?
No.
No. Which one?
That one.
That one, right?
Yeah.
Okay. That one there. That one and the H I'm holding here. You see how they're anticoplanar? Okay. Now, are they cis or trans? If this iodine is straight up and this H is straight down, they're trans, right? Yeah. Which one over here is trans? That one. You're going to eliminate these two. Those are the two that can be anticoplanar. And that's the driving force here. That elimination requirement is going to beat out the other one. Now, an H is an H. But I'm going to clarify which H actually remains. Which H remains after the elimination? HB. I'm going to put it there just for that clarification, that if we consider that for some reason if those H's were different, it would be the one that's HB that would remain. It's HC that will get eliminated in the E2 elimination. This is another example where, did we get the most stable product? S. No. No, this reaction gives a less stable product, the estimated product, because of the stereochemical requirement for E2 elimination. Making sense? Okay, you can work the others. There's a question down here. Because look, this has to eliminate when the iodine is axial. Is that the best confirmation, or could this actually be equatorial? The equatorial may actually be the better confirmation. Okay? But if it's in the equatorial position, it can eliminate. And it has to take time to go back to the other confirmation. If it has to do that, it's going to be slow. That's sort of what this is getting at down here. Which reaction would be faster? The answer is ultimately in which one can the leaving group more readily be, or more often be axial? That's really the question. Because we know it has to be axial to eliminate. If you've got a compound where the iodine really wants to be equatorial, it's going to be slow to eliminate. Okay, so let's start thinking more about substitution versus elimination. If both can occur, which one's going to take place? All right, let's look at some of these types of considerations. First is, heat favors elimination, okay, due to entropy. We've mentioned this several times before. If you take this and maybe just heat it in water, probably going to get an E2 product. I'm sorry, E1 product. We can eliminate HBR. The water really did nothing here. The water was just maybe solvent, okay? That's an E1 reaction. Everybody agrees E1? I haven't seen any strong base around after E1, correct? Okay. But as we mentioned before, if you ignore water, one molecule becomes two, right? One molecule becomes two. And so that's driven by entropy. And haven't we said many times that the temperature magnify entropy term? Okay? So the more you heat, the more you're going to sort of magnify this favorable entropy. Now SN1, on the other hand, that would be two molecules going to two. So does that look like it's favorable by entropy? No, not as much as one going to two. So heating this is really not going to do you much good. You're magnifying a sort of a entropy term that is not really good. It's not maybe not bad, but it's heat will magnify this 1 to 2 favorable entropy. Heat thus favors elimination. All right. You got to be careful with this, though, guys. I see students say, "Oh, heat, it's got to be elimination." Did we say that? No, we said heat. Oh, how do we say that? Sometimes a substitution may require heat. Well, that's okay. Maybe a substitution requires you heat it at 100 degrees. Yeah, that's reasonable. But if you heat it to 200, all of a sudden elimination starts becoming preferred. Does that make sense on base what we just said? More heat favors elimination. You gotta be careful. It doesn't mean that anytime you see heat, it's elimination. There may be other things going on. It's more of a relative thing. Number 2, involvement of a good nucleophile will favor substitution, while a poor nucleophile will typically favor elimination. Look at this. If you take this alcohol, have you ever used that alcohol before?
Yes.
I think that's
The last
TMO
time.
alcohol in it. From last week. If you react it with HBR, you get a SM1. You did this before last week, right? Okay. But if you react it with HF, the most likely product is going to be the elimination product, E1. Why? This is an example of nucleophile. Which is a better nucleophile, Br minus or F minus?
Br minus.
Br minus. The better nucleophile is going to be more prone to giving you substitution. Okay? F minus is a poor nucleophile. That means it doesn't like to attack carbons. But it will act as a base and remove a beta hydrogen. Okay? So the difference in nucleophile strength explains these two different outcomes. The first step of both of these reactions is what? First off, do we have a good leaving group?
You gotta.
No? How do you make a better leaving group?
Protonate it.
We have a strong acid, protonate. Yeah, in both
HBR.
cases we have strong acid. After you protonate, what happens?
The H2O leaves and it's replaced by the Br.
What's on tertiary carbon? Are you going to do a backside attack on a tertiary carbon?
No.
No. So what could happen? The only thing that can happen is
Leaving group leaves.
leaving group leaves. And when that happens, what do you form?
Carbocation.
You form this. But here is the difference. Br minus will add to the carbocation in a nucleophilic manner. F won't do it. Instead, what will F do? F instead takes a beta hydrogen and puts in the pi bond in the fast step, right? That's the second step of an E1. Because F just doesn't like to add to carbons as much. F is actually, which is a better base, Br minus or F minus? Actually, F minus. We talked about that before. Yeah, it's a better base. That's not a strong base. Do you consider F minus a strong base?
No.
It's an anion. It can't be strong. If it was a strong base, then HF wouldn't be a strong acid. Okay? Just like Cl minus. You can't call Cl minus a strong base. Then HCl wouldn't be a strong acid if Cl minus was a strong base. Okay? There we go. Look down here. A common reaction of alcohols is to dehydrate them using strong acid. But you've got to use a strong acid like sulfuric acid. Minus H2O. Does everybody agree that if you go from here to here, you have to remove water from here, H2O? Yeah, it's missing H2O. We remove water, we can call this a dehydration reaction.
Question: would the strong acid be considered anhydrous? The strong acid is taking
Well,
away
some
water.
can be anhydrous, some not. HCl used in lab last week is aqueous. Why do you ask?
Because I know normally, because we dried it in lab last time, we used like a salt to get rid of the water. It
That was after the reaction was over, though. That was doing workup of the product we didn't want any water in our product. But the reaction was in an aqueous environment. You used aqueous HCl. Now, HF can be actually dry. HCl can be dry, but when it's dry, it's a gas. We didn't use HCl gas last week. We used HCl with hydrochloric acid aqueous. Dry HCl is a gas. The common reaction is dehydration of an alcohol by an E1 mechanism. E1. It's the same exact thing guys up there with HF, except H2SO4 is a much more common acid for this. and you're going to make carbocation. Once you make carbocation, what can attack the carbocation? What have we said about the sulfate anion? Will it ever attack anything in this class? No. So there's no nucleophile here. But something will take the beta hydrogen, either the sulfate anion, or you can just show water taking it. Basically, there's no nucleophile there, so all I can do is eliminate. It's usually the same as HF if you consider F minus being this non-nucleophilic. On the other hand, if you try to do this with HI, you're going to get a substitution product. Why? Because once you form the carbocation, I minus is such a good nucleophile, it'll add to the carbocation and give you that chemistry. In the end, what did we say? Good nucleophiles will favor substitution. Poor nucleophiles will favor elimination. This is a very common reaction, a dehydration of an alcohol. We'll certainly cover this again in organic 2. And when I do it, I'll basically just remind you of what we did in organic 1. It's just a standard D1 mechanism for dehydration. All right? Common reaction of alcohols, though. Here's a mechanism for you to work on. All right? Number 3, a more sterically hindered base will favor elimination over substitution. Now, we kind of already said this. I'll approach it this way. Say you want to do this elimination here. Everybody agree it's an elimination reaction? What base would you use? What base would you use? You want to get a high yield so you can get a good grade or get a pay raise or something, or just get some intellectual satisfaction of accomplishing a good yield. Which base would you choose? Anybody? You would choose ammonia. Nobody? Who would choose sodium hydroxide? Why?
Because it is a strong base. We're doing elimination, right?
Okay, you mentioned strong base.
And
Aren't all these 3 strong bases?
yeah, but that hydroxide is small, right? And we have this. Oh no, but it's not.
So, how many different elimination products are possible? Is there another alkene we can make other than that? Forget about the ring. Is there another alkene?
Yes, sir.
There's only one beta hydrogen. There's only one alkene to make. We don't have states for Hoffman. There's only one theoretical product.
So does it matter then?
It does. We got to figure out the reason why it matters. What if we used ammonia? Is it going to eliminate, or could ammonia come in here and do this? Why not? It's a good nucleophile, right? Can it not do an SN2? Sure. What about hydroxide? Can hydroxide
Yes.
do that as well? Bam! The question here is really, we don't want SN2, we want elimination. Which base is going to favor elimination?
The more sterically hindered.
More sterically hindered. Why? Because sterics hurts SN2. If you don't want SN2, use something that hurts that reaction. This over here will be terbutoxide, sodium terbutoxide. If you look at the previous handout, we mentioned right under triethylamine. We also mentioned that's commonly used as a base for E2. Because it's so sterically hindered, this is going to be more difficult. Instead, it will be like, okay, well, I'll take the H then. I'll show you. And I'll kick you off that way. I'll take the H. And those electrons can come in and kick you off. And doesn't that give the alkene when you do that? Take the beta H. More sterically hindered base. What did we say? A more sterically hindered base will favor elimination over substitution. Clever ways to make ionization to a carbocation faster. Lewis acids. Silver ion. Silver ion was part of the pre-lab last week. We'll mention this as we continue on Wednesday. Wednesday we'll have a quiz over substitution. Okay? Yeah, I think we can maybe not put elimination on there, unless you think we should.
No.
Because the test is coming soon, might need to start, okay. I think we can just focus on substitution. We finished up substitution. Okay. Various things, including synthesis, mechanisms, various points. Have a good day, guys.